for such a long time is that doctors, both radiologists and clinicians, do not have enough ability to play with AI. Right? Everybody is talking about it, but it is very non-trivial as Sir articulated initially. There are hardware issues, legal issues. There's so much contracting, etc., that goes into it. How do you even experiment with it? How do you even know what exists out there? So that's again, one challenge. Of course, we are solving that challenge, but these are just my thoughts that because deep learning fundamentally makes unpredictable mistakes, it needs human oversight today, but there is still a trend towards basically machines doing the laborious work, and radiologists focusing on more important things and maybe getting exponentially more productive in the process.
Thank you, Dr. Mahajan. Now, yeah, we can see the questionnaire on screen. Now, the last one uh, that is that I was going to ask Group Captain Rahim sir first, but I think that question applies to everyone. So we start with Rahim sir. Is explainability and transparency a necessary condition for adoption of AI models?
Yeah, I would definitely say yes, because I was just trying to think when we are talking about explainability and transparency as a necessary condition for adoption of AI models, whether it is from the patient's perspective or from a referring doctor or clinician's perspective or from regulatory perspective. See, what we are actually saying is we want to have build a trust, to have a trust, because human beings are intrinsically trust driven. So we tend to go by either we trust a model or a trust a person or we don't trust a person. Unlike machines which have a sort of a layered levels of trust. So if I have to put this radiologist analogy, so when I finished my radiology and I went to hospital as a young radiologist, how did I build trust in the clinician? So first thing they said is, okay, you have passed MD exam. That means that is one level of certification I have. So that gives us a level of baseline trust. So that if I am signing a report compared to a person who doesn't have an MD degree, so there's a little bit of trust has come into the clinician. So I'm applying the same analogy to AI models. When a model is sort of accredited or certified by a regulatory agency like FDA or CE or any other regulatory agency as software as a medical device model. So that is what is presently being followed. So initially AI models have been used as something like medical devices in the category of software as a medical device. From there, now slowly all the regulators across the world, they are moving into a system where it is like a concurrent or it's a continuous regulatory or a accreditation mechanism, like where AI model, the whole life cycle is being regulated and monitored, not right from the development stage and even after the model has been approved. Earlier it used to be like a closed model. That means once a version of a model has been approved, developer cannot do any changes. But from that perspective, now regulators are moving to a situation where the system is already built in place, where the developer is telling how he is going to change modifications, when is he going to update, what are the parameters he is going to monitor. So this kind of, over a period of time, I see this kind of regulatory certification will build a minimum level of trust in the models. Second level is in the initial stages, the clinicians or the patient, they want explainability. Like this, if I give a same analogy of me, when I used to write as an initial young radiologist, my report used to be long, 1 page, 2 page, explaining all my findings, like why I'm saying this is there, that is not there, before I say pneumonia is there in the final impression. So I had to explain to the whoever is consuming the report why I am saying this is pneumonia or not pneumonia. The same applies to AI models also. In the initial stages, they have to be able to convince every stakeholder, whether it is a patient, whether it is a referring doctor, whether it is a regulator or anybody, but even a fellow radiologist. So that is what we are looking at. So explainability and whether you can use it different mechanisms, either heat maps or a bounding box or a image overlay. That means on an original image, the AI generated image is sort of overlaid so that we can exactly see when it is saying a pneumonia patch, where exactly it is picking up the pneumonia patch. So this kind of explainability models will improve the trust in the system. So as we move up the chain, so the trust will come to a situation where, like, if HOD radiologist is signing a report, he may not write everything. He will just say the chest X-ray is normal, or is this pneumonia. So that means, so once we reach that kind of level of trust, so we are looking at more from a point of view of ease of access, or we work more the trust. So I know it's a long way, and we are moving on that direction. So once that necessary with period of time, the trust will come into the picture. So all these issues will be sorted out. So just I want to touch upon before I end on the transparency. There is slight difference between explainability and transparency. When you say transparency in AML, that means we expect the developer and the to explain on what data he has trained his model, what was his algorithm framework, whether he is willing to keep it as open source or it is a closed secret, or what is the kind of post market surveillance strategy he has, so that he gets a real-time feedback from the environment, where the system is doing good, where the system is going wrong, so that that necessary feedback in ideal situation flow back to the regulator as well as the developer, so that they can build upon and they can rectify those mistakes. So this is what I feel the importance of explainability and transparency for adoption AI models. Thank you.
The Thank you, Rahim sir. This remaining question in this session, that how to ensure AI models in radiology are free of bias and are representative in the real world. This is not pertaining just to radiology, but to any discipline which employs AI models. So, as an example of this, let's say we develop an AI model which recognizes something like color from the color of the skin of the face or something like that. Now, the problem in this kind of models is there are always variety of faces. So this diversity, including them in the training set, is a difficult challenge. So this question I'd like to ask Brigadier Muthukrishnan sir, HOD Medicine, that when do we know that we have trained enough? Should we consider local variations, global variations, and how much variability in the data in our training? Is there any specific direction we should go as developers of AI models, sir?
No, I think one of the previous panelists did mention that relevance of any of these models would depend on where the initial process of development has happened. The data that you use to develop the model should come from the area where you're going to eventually apply it. So for example, there are a lot of time there are racial differences, like you gave an example of pallor. So there are those racial differences in appearance or in pallor, which may be taken as normal in those areas and taken as abnormal in another area. So I think where the initial data which has happened for development of the AI model validation will matter. And then of course, subsequent learning that happens with repeated use of such models and incorporation of local the data where it's going to be applied will also help in making it more representative of where it's going to be used. But I'll just add one point on this, that too much of dependence on AI, especially when it comes to picking up these kind of signs, which are very relevant in diagnosis, will have to come with a clinician as supervisor for these kind of models. So probably if there is a supervisor, the clinician, who's using this AI as a tool, the same pallor that the machine is now looking at with repeated reconfirmation by the clinician would make the AI model more robust with all the learning aspect that will get incorporated with repeated usage.
Sir. So with that, we conclude this session on radiology. Dr. Vidu, thanks for joining us, and thanks to all the panelists. We have collected the requisite action points for preparing our draft guidelines in the area of radiology. And Dr. Vidu, we hope to work with you soon. So
Thank you, sir. Thank you.
the next session is on the development part of AI with statisticians and computer scientists. Good morning, Professor Nishit and Dr. Vineet. Good morning.
Hi, good morning to all.
Professor Nishit Srivastava sir has joined us. I'm sure sir was listening intently to our discussion on these points, and sir is uh, alumnus of the University of Minnesota and IIT Madras, and presently in Department of Computer Science in IIT Kanpur. His area of interest is not just AI but cognition in general, and his research papers are an eye-opener. Dr. Vineet Kumar Kamal has joined us from Department of Biostats, AIMS Kalyani. He is a former scientist at Institute of ICMR, Indian Institute of Epidemiology, NIE, National Institute of Epidemiology. So, and we have two very senior epidemiologists here with us, Brigadier VK Bhatti sir. He is the HOD of PSM department at AFMC Pune, and Surgeon Captain Saurabh Bogde sir, who is the OIC of Medical Research Unit at AFMC Pune. So the questions to Professor Nishit sir. So the crux of the issue, sample size for training and testing AI models, sir.
Okay, so this question used to have a pretty straightforward answer about 20 years ago. The rule of thumb that we used to adopt was that you take as many um, data points as the natural exponent of the number of parameters in your model. So if you have a, a 2-parameter model, you would take about 100 observations were enough. If you have a 10-parameter model, then you need about 10 billion observations. And this is what was sort of the rule of thumb. And it used to work pretty well because machine learning models back in the day used to be pretty simple. But then, now that we have deep learning with us and models routinely have billions of parameters, this has become a much harder challenge to address, and theory is not really a very good guide at this point. And so at this point,
when you say parameters, just for the clarification of the house, sir, you mean trainable parameters in the model, sir?
yes,
Right, sir. Not clinical parameters, but the parameters inside the model, what sir is talking about.
yes, so degrees of freedom. So what can you allow to change in the model? And so at this point, even the best people that one can think of, the only rule of thumb is that the more the better. There really is no other guideline. Certainly, if you have, let's say we're doing radiology or any computer vision related applications, and you're doing 512 cross 512 images, and you're trying to do some sort of object recognition in that, you will not have any kind of success unless you have at least 100,000 observations. That is something that can be said. If you sort of have a 32 cross 32, then you might have some success with even smaller samples, like let's say 1,000, 5,000 observations. But for 512 cross 512 images, you need much more. And but these are all empirical observations. In some cases, the problems are actually simple, and you can get reasonable results even with less data. So it's really alchemy at this point. The theoretical guidelines don't really apply. So I don't think there's a good answer. But the heuristic that one can use is that the more the better.
Sir, so this is one of the key points that I keep facing during each of my presentations whenever I started talking about AI, that what is the requisite sample size and how we handle it. So I thought I should put that question to you first, sir. So next issue is the variety in training. So how do